All right. So we're doing nuclear chemistry. And again, if you weren't here, I'm going to make your worksheets worth 6 points from now on. And then your midterm exams will each be worth 75 points. That does leave you all with a bonus point at the end, which is wonderful, or maybe there's somewhere else. All right. So I'm dressed as Captain America because if you know your comic books, he's here, boys and girls, to teach you about nuclear chemistry. And we all hear the word nuclear chemistry and we think it's scary and stuff, but nuclear chemistry just is the study of the nucleus. It is also called radioactivity. This would be a serious bonus point. And so if somebody who's here knows it, you get a bonus point. And if they don't, then this will be your send an email before the next lesson, the next lecture, and tell me who coined the term radioactivity and why. Does anybody know? So you can all now get the bonus point. So you can Google it. And why? Why did they use that term? It's actually really cool. So nuclear chemistry is not just the study of the nucleus, it is the study of an unstable nucleus. And I'm dressed as Captain America because this is kind of what they did to me, to make me big and strong. So some nuclei are stable and some are not. And it has to do with the proton to neutron ratio. It was in my Captain America's sleuth mode, and I went to school and got a whole bunch more pens. So that's why you can see my pens today. So these, remember, protons and neutrons. So the ratio tells you if it's going to be stable or not. For your purposes, if we're working with this chapter, which is your homework for Wednesday, and your worksheet, your study set and your worksheet, they're going to be unstable nuclei. And then when we're not working with this, it is stable, but it is a ratio. Sometimes it's 1 to 1, and sometimes once you get to too many protons, they just all become unstable. So these two together, if you recall, we call them nucleons. Just means they're in the nucleus. And, oh, another term to review from last week is the term isotope. So, here we go. Maybe this will be the bonus point for in class. Everybody has their buzzer. Does anybody remember? Can they define for me what an isotope is? So the prefix iso means same. So there's something that is the same of an isotope and something that is different.
Isn't it that they all have the same number of electrons and then different number of neutrons?
So you almost got it. That was Kaylee?
Yeah.
Same protons.
Instead of, so Kaylee,
same
instead
protons
of,
and neutrons.
yeah, it's Kaylee. You guys have to, all the rest have to go away. Kaylee, come back.
Hi.
I have to figure out how to get Zoom to make the person I want to come back. So Kaylee, yeah, you have to kind of grunt or something. Yeah, instead of saying electrons, I'm going to give it to Kaylee. Remember, we're not talking about electrons because the electrons are not in, sorry, hopefully you guys don't see what I see. The electrons aren't in the nucleus, and so this is all about the nucleus. So instead of saying same electrons, we would want to say same
Protons.
You got it. Which the rest of you, a lot of you are trying to say also. So Kaylee gets our bonus point today. And the rest of you can. You just have to email me that answer. So the example here, let's do this one. Can you see? Still, it looks like it. That these are both isotopes of carbon. So they both are symbolized by C because they both have 6 protons. You can always get that. Captain America, of course, knows it because he got an A++ in chemistry. But your handy dandy periodic table, atomic number is always there. And then these are the mass numbers. Very important today because they are our nucleons. This is stable. The stable ones are the ones that are close to that average. Remember we did problems last week about that average was the most abundant? The most abundant are the ones that are stable, and this one is unstable. And I'm pretty sure we have a question either today or in our study set about carbon-14. So all the elements have isotopes, and some of the isotopes are stable and some are not. So hydrogen, there is our first element, there's H1, there's H2, there's H3. H1 and H2 are actually stable. H3, this ratio just gets all wonky, and that's an official chemistry term. So again, I will tell you, and let's see, what's the next term I wanted to talk about? Okay. There's my eraser. All right, so we're talking about unstable isotopes. And nuclear chemistry is, oh, we'll write Kaylee's name over here so I remember. Kaylee. These are the symbols, alpha, beta, and gamma. So you'll hear me say the word alpha, but that's a symbol. It looks like a fish, and it is. And then gamma's bad news because it's like a dead fish. It's dying. Gamma's the one that like messed up my really good friend Bruce Banner. That was gamma rays. Do not play with gamma rays. You don't want to be like Bruce. Bruce has some serious issues with his talking, his anger issues. All right, the symbol is more than just this, and what we have to talk about, we'll do alpha first, is alpha's full symbol is 4,2. So this is a review from some info that we already did, that your lovely teacher already showed you. The upper number is the mass number, and it is the number of nucleons. The protons plus the neutrons. Remember, that number is not on the periodic table. It has to be a whole number. We're counting, we're only dealing with protons and neutrons. Right? And then this lower number is the atomic number. And the atomic number tells you what, boys and girls?
Proton?
It tells you the protons. So just the protons. So this particle is made up of 2 protons and 2 neutrons. What that means, so I'll make my protons can be the black, and the neutrons will be the open circles. It's all together, they're not separate. It's all one package. That's what an alpha particle is. Now, on the periodic table, I should have told you that when I was going to get my dog, that you should get your periodic table out. So if you don't, it's chemistry, you should always come with your periodic table. What element has 2 protons?
The helium.
Helium, thank you, Philip. He's the only voice I don't need to like look at the screen for. So this is the alternative symbol, would be helium with a 4. We are with nuclear chemistry, we are going to always show both numbers, and you'll see why in a few moments. So this is the alternative symbol. I personally, as Captain America, where's my alter ego? I prefer this, because when we see one of these symbols, rather than their alternate symbol, their alternate ego, this is like the Hulk. This is saying warning, 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 danger. And this is like, oh, it's a helium. And we don't realize that's not a good thing. All right, beta gets a 0 and a -1. How can you be a -1? Well, the alternate symbol is a 0, -1 E. It is just an electron. It's not just an electron. It is a high speed. You know, this is a serious understatement because it's not like 50 miles an hour. This is like 55 billion miles an hour. It's a high speed electron. It is moving, like all electrons are moving crazy. But really the question is, how can it be an electron? Because we're talking about an unstable nucleus. And the electrons aren't in the nuclei. But it turns out where we currently are in our thinking and understanding, protons and neutrons are not the most basic type of particle. You can actually split a proton. You can split a neutron. So you don't need to know this piece. But what a beta particle is when a neutron breaks down. It has a meltdown. Just couldn't take it anymore. All right, and it becomes a proton plus a beta particle. So the neutron is really made up of a proton and an electron. This beta particle, though, because it gets ejected from the nucleus, it's moving like crazy. The neutron just basically becomes a proton. The proton stays in the nuclei because nuclei have protons and neutrons. So a neutron just changes into a proton. I wanted to mention, I have to see what my chart says, is, well, we'll come back to that. All right, gamma, symbol is 0, 0. We're going to talk about this more next Monday. It is no mass, no charge. What is it? It's a plane? It's a bird? What is it? It is high, like serious high frequency vibrations. It is not matter at all. It is light that is moving crazy high. This is higher than ultraviolet. This is higher than X-rays. So I'm pretty sure you've all heard of X-rays. You're familiar with X-rays. So this is what my friend Bruce Banner was working with, was gamma rays. And you should not work with gamma rays. So my friend Joyce, your teacher, she actually worked with gamma rays, but it was like deep in this basement at Penn State. This is my undergrad years. And all the science labs used to be connected by these underground pathways, and deep, deep, deep was this place, and you would put your sample in, and it was just surrounded by like layers and layers and layers of lead, and you'd put your sample in, and then you'd wait while the gamma rays did their thing, but you were surrounded by so many layers of lead, you were fine. And there was this one vending machine, and that vending machine was already broken because everybody kicked it because you were there for 15 minutes bored. Anyway, yeah, there are probably dragons and gnomes down there too. All right, so a couple more things about these guys. They are known as ionizing radiation. We can erase that part. They knock, what it means is they knock electrons out of orbit. So electrons are normally going round and round and round and round the nuclei, and these guys knock them out. We're going to talk about electrons next week. This ultraviolet light also is a type of ionizing radiation. So we know if we get too much on our skin, we can cause skin damage. This specifically, though, this ionizing radiation came from an unstable nuclei. Every atom has a nuclei, and if it's unstable, it releases ionizing radiation, alpha, beta, or gamma. I talked about in that video you watched for the lab, alpha and beta is what Rutherford won his Nobel Prize for, was studies with alpha and beta particles. And then gamma has no mass and no charge. Why it can, electrons are matter, they're really infinitesimally small matter, is if you have a high enough frequency, you can actually cause changes to matter, which is really phenomenal to think about. All right, so the question says, which has the greatest ionizing potential? Ionizing potential means which can cause the most damage. So alpha, beta, or gamma. See, I should do this as a poll if I could get my act together. Which one's going to cause the most damage? So I had it's actually a question in your homework that it was a physics teacher said you had 3 cookies. You had an alpha cookie, a beta cookie, and a gamma cookie. Which one do you never ever eat because it's going to cause so much damage?
Gamma.
So, no, everybody says gamma. Thank you for being so brave to answer. I was waiting for a brave soul, and everybody gets it wrong every time. I would have too. Everybody picks gamma because they go, it's high frequency vibrations. But the reason it's not, so actually, you can go back for a second. So Christie's would have been right if it had been the next question where it says, which one has the greatest penetration? Gamma, it goes right through you. But because it has no mass and no charge, it goes through fast and probably doesn't cause any problem. The greatest damage is the alpha. In fact, they used to, not long ago, when you went in with a mass tumor, so like breast tumor, or a prostate tumor, which is a mass tumor as opposed to blood cancers, they would actually implant alpha emitters into the tumor, thinking the alpha particles would destroy the tumor. The problem is it destroys the tissue around it. But the reason this is the most damaging is size matters. This thing is huge. Sorry, Captain America gets really excited. And there's actually the picture, if you're able to print the notes, or you can look at the notes, it shows you an alpha, a beta, and a gamma. Beta does have a mass. Electrons have a mass. And this is, I had an example. Oh, there, my good friend, Tom and Jerry. So you guys all know Tom and Jerry, no matter what culture you're from. Like when I was in Nepal, everybody watched Tom and Jerry, like anywhere I've gone. Anyway, I talk about it that the electron is like a mouse. And I don't know where my other one is. Ganesh. Okay. Well, we'll have to go with, it's supposed to be an elephant, but I can't find my elephant right now because of the mask. But like a camel. The alpha is like an elephant or a ginormous camel or a Tyrannosaurus Rex. So if we were all in the classroom right now and a mouse ran in the classroom, is the mouse going to cause much damage? Might scare some people, but there's probably a lot of mice in the classroom right now because nobody's in the classroom. But if a Tyrannosaurus Rex or an elephant ran through your house, it's going to cause damage. So the size of this is very frightening. The good news, your skin protects you. Alpha particles cannot get through your skin. This is why when they implant people with alpha particles, that's really scary because they can't leave them. They're stuck inside. So your skin, the protection, I think that was the last what blocks it? A piece of paper or your skin blocks it. Beta is really thick plastic. Plastic's wonderful because you can see through it. You don't have to have superpowers. And gamma Oh, you've all been probably at some point to a dentist's office. Yeah, you have to have lead. So they used to put lead aprons on us when they took x-rays. That was Bruce Banner's mistake. He didn't have any lead on when he got exposed to the gamma rays. If you go, cosmic rays are actually higher. And so our Earth atmosphere protects us. But if you go to the moon, the astronauts had to have the gold, right? Their shields were gold because gold is actually denser than lead. Here's a bonus question. Oh, so many bonus questions for your class. You guys are getting spoiled. Does anybody know what element's the densest? Can't answer both, but you can email me one or the other. So the first one or this one. What's the densest element on the periodic table? There's actually something denser than gold, but gold is denser than lead. There's actually only, I think, 2 elements.
Oh.
Go ahead, Tatum.
Is it osmium?
Yeah, osmium is the densest. So if you have your periodic table, osmium is number 76. And so the density funnels into there. So as you move in that direction, you become denser. If you know the old pencils, you may know somebody who wrote I'm sorry, not pencils, ballpoint pens. People can actually write with a true ballpoint pen. They were made with osmium tips. You would get one in your lifetime and you get refill cartridges because you wouldn't break it. Or if you know what a phonograph is, that's back from my day. And the needles would be made with osmium and then they wouldn't break. So most of us had really cheap phonographs and the needles broke because we were little kids and we didn't have lots of money. All right. You know, there's some notes on there about exposure. You're always going to have some exposure. Your body, the earth, the atmosphere does protect us from a lot. Yeah, it's the mammogram one, they've changed mammograms, they've changed x-rays, and so the exposure has become less and less. The thing that's a little crazy, oh yeah, the CAT scan is insane. And we do, I've never had a CAT scan. Electronics, I have no electronics in my bedroom. People sleep with electronics all around them, and you're getting exposed to lots of interesting waves, not necessarily these, but ones that do interfere with melatonin. And cigarettes is a huge number. By the way, they're in what's called millirems. At first, it says little m and then rems, but cigarettes actually, because the soil in Tennessee and on the East Coast where most tobacco is grown is actually slightly radioactive, and it's in all the tobacco. So yeah, don't smoke. Smoking is not a good thing. All right, questions. I'm going to switch and share my screen, and then I can see again. This is it. All right. So I have to write Tatum's name up here so I remember. I really am impressed. Oh, yeah, you know, it is the month of October. And Goodwill is open. So I'm like expecting more costumes here from you guys. Oh, there's bonus points you could get. There will be certain themes that we'll start running into. So the alpha particle, you can use pink. Just again, is our symbol is alpha with a 4 and a 2. The 4 is the mass, the 2 is the protons. The alternate symbol is the helium nucleus. I know I didn't give you a lot of room and I didn't mention that up there. So the difference and why I don't like using this symbol, and you won't really see me using it today, is when we usually show a symbol, when we did them last week for our study set and when I was teaching that, we had protons, neutrons, and electrons. We are now only talking about the nucleus, which is really bizarre because the beta particle is a high-speed electron. And again, it's why I don't like this alternate symbol, but it's been ejected from the nucleus. It's a neutron, changes into a proton. You don't need to know this, but it is actually really cool. And gamma is just shown as the fish has sunk. Gamma is the greatest penetration. It's going to go right through you. The chance that it runs into something is extremely slim, like that 99.999% thing. The greatest ionizing potential means damage, and that is the alpha. That is the Tyrannosaurus Rex running through your body, causing issues. Which brings us, that picture down here, there's a play that was really famous about the Radium girls. So Radium, there's so much history with this. We just do a whole history class. Radium is a solid, and it is found in certain parts of the country. There's something called the Reading Belt. You guys in this part of the country call it the Reading Belt, but it's Reading, Pennsylvania. There's a lot of radium in the soil around the Great Lakes and on the west side of our town. So certain parts of Portland from the big floods that went through like 1 billion years ago. And what happens though is radium, it glows naturally, and they used it. These girls painted watches, so it was before the digital age, and they could make a watch glow. So that's what she's holding there, is a watch. And so they'd paint it, but to make their paintbrush very thin, they would lick the paintbrush, and then they would paint it with this radioactive paint. But it was before they knew what radioactivity, the problems of it. And so every time they licked the brush, they got radioactivity on their tongue, and a high number of these girls got cancer and died in their throat, in their mouth, some terrible stuff. And it was because of the radioactivity. So it is your best source, your best defense, besides not smoking, is to walk away. The further you're away, and that is, you walk away. Some other interesting thing, Chernobyl, which many of you don't know because you weren't alive, but Chernobyl was in Ukraine. It was a nuclear power plant that they were running a test and something went wonky, and there was a release of radioactivity. The area is now a national park, like 30 years later, as of last year, because there is some plant life that doesn't exist anywhere else on the planet, and there are some minerals that have formed, like rock formations, because of this partial meltdown. So, right, from good and bad, what is good, what is bad? All right, there are some other particles we're going to run into on the next page. So a positron is the antithesis of a beta particle, meaning it's a positive instead of a negative. So what it is, it's a proton that becomes a neutron plus a positron. That might make more sense after the next page, but there's always a student who finds these pieces interesting and others who don't care. The symbol for a neutron and proton are lowercase, N and P, but we have to put the full symbol. So they both will get a 1 on top because they're one nucleon. The neutron gets a 0 below, so it's a 1 over 0 because there's no protons. And the proton gets a 1, so it's a 1, 1, because it's 1 proton, 1 nucleon. So again, our symbol, the top number, oops, sorry. Oh, I don't know. I'm sorry. I'm trying. Let's just do the next page. I was trying to think of a way to say it better. Yeah, let's just look at the next page unless somebody has a question. The biggest thing we're going to be doing is writing nuclear equations. This will change quite a bit next week. It all becomes about the electron. and chemical reactivity is the electron. The 20th century is called the nuclear age because it's when we learned that we could split the nucleus. So you can have alpha or beta decay, and I will always tell you which one is happening. So how we do these is we write the symbol for the element that we're talking about, and we're going to show the atomic number. So we find uranium. It's a really large mass. So it's going to be down at the bottom, and it's there. It's number 92. This is the mass number. You will always be given the mass number. So 234 over 92. For uranium-235, same thing, 235 over 92. They're both uranium. They have different masses. So you're all going, oh, they're isotopes. All right, yes, they are. We're going to do a decay. Decay means it's breaking down. The nucleus was unstable. So again, I will tell you, it's going to go through which type of decay. So you write the particle. So there's my alpha particle, and there's my beta particle. Now, it always becomes something else. So the alpha or beta particle are released, and they go and cause their damage. The alpha particle causes damage because it's massive. It's 2 protons and 2 neutrons. It is the Tyrannosaurus Rex. Anything it runs into, it's just gonna stomp through there. It's like my friend Bruce Banner. It's like the Hulk. The beta particle, it's just a itty bitty little electron, but it is moving so freaking fast and so much chaos. So it'd be like if I wound any of you up a zillion times and then let you go, right? Gave you like the caffeine with 20 shots of espresso or something, and you just go crazy and you just start running into everything. So this is how this works. The numbers on top have to be, this is like an equal sign. Think of it like that. The arrow, we show it as an arrow. Think of it like an equal sign. The numbers on top have to be equal. So this must be a 230 because we have 4 plus 230 equals 234. And the same would be for the bottom. 92 is 2 plus 90. Now we look at our periodic table, handy dandy periodic table, your best friend. You're not looking for the top number because that can change. You're looking at this lower number and you're finding element 90, which was named after, oh, my good friend Thor. You know, I have to tell you, I never saw the last Marvel movie, so I have no idea what happened, and I don't want to know because I don't care, so don't ruin it for me, even though I'll never see it. All right. So for the next one, 235 is equal. You can write the equal 0 plus 235. Mass does not change with beta decay, but the atomic number does. So my question, what's my new atomic number?
93.
It is. Thank you. Woohoo. Because -1 plus 93 is 92. And then we go and find number 93, and it is NP. This is how I can look like I'm really smart because the periodic table has all the answers in the universe to it. So uranium was discovered right before the planet Uranus was discovered. And so they named the planet after the element because they thought it was really cool. I think that's right, somehow in there. Anyway, the next planet was Neptune, the next one was Pluto, and so on the periodic table, they named them in that order of the planets. So the order of the planets, by the way, if you go outside right after class and look directly to the south, you will see Jupiter and Saturn. They're still in alignment. You'll see Mars rising because it's rising in the east, setting in the west, but we can't see it in the morning because we have all that fog. All right, so there's our answer. So now we're going to do it again. I sometimes talk in hopes that you guys will try those. So I'm going to pause the video for 5, well, yeah. I'm going to give you guys a moment. Pause. I'm going to go through it. I know you didn't have time to do all of them, but so writing the symbol is I-131. And then we find iodine again on your periodic table. It will always have that, whichever periodic table you're using. So iodine is number 53. And with decay, it's breaking apart and you're losing the beta particle. So I usually write the particle first. You can write it second. It doesn't matter the order that you write it in. So I go, okay, it loses the beta particle and now it becomes something new. Now with beta decay, the mass does not change. So it's still 131. But this is, I think, what you were saying, Tiffany. The atomic number actually always moves up one. And that is because back, I don't know if you can see, when I talked previously, beta decay is a neutron becoming a proton. So it becomes number 54, which is xenon. Just show the symbol. So the -1 plus 54 gives us 53. So the arrow is the equal sign. All right, PO, polonium, was named for Poland by Marie Curie. She discovered it. It was quite a bold name since Poland did not exist at the time. The size of the mass tells you it's down at the bottom somewhere in the periodic table. It's number 84. I'm telling you it goes through alpha decay. This is not a stable form. You can see on the periodic table 209. All right, so our new mass must be 206. 206 plus 4 is 210. So alpha particles are massive weight loss. Whatever you started with, lost for it in its mass. And its atomic number, it's now down by 2. So 2 plus 82 is 84, and that is, should be PB, yes, lead, so plumbum. Right, and then sodium, hopefully this is where I can't emphasize enough learning the first 36 elements. Not necessarily in order, but that way when you see sodium, you just know that's Na. You don't have to keep looking for names and stuff. The PO, you don't need to know the name of those guys, but sodium, it's 22, and actually it's, and then number 11. You can see on the periodic table, it's closest to 23. This is all about instability. And so 22, we're going to be dealing not with these numbers on the periodic table. We do want the 11. That tells us it's sodium. Keep that in mind. You'll all ask me that on Wednesday. And I tell you it's positron. The word emission means to emit. So again, we're losing it. A positron is the antimatter of a beta particle. Same mass, opposite charge. The theory is if the two came together, we would not exist. But do we exist anymore? We live in this little virtual world, right? So mass, again, does not change. And this time, it's a 10. So this is back to what Tiffany asked. And this, so it's a +1, +1 and 10. These two are on the side we're adding. Has to equal the one on the original side. Number 10 is neon, so Ne. Symbols I do care about. First letter is capital, second letter is lowercase. All right. You do need to fill in your lower numbers, so oxygen's an 8. That's my equal sign, and if you want, you can make it an equal sign. I'm okay with that right now. My new mass is 1 up here, so 14 plus 1 is 15, and my new atomic number is 1. So there's 2 answers. You can write H, because that is element number 1, and that you would get full credit, or it's a proton. So remember, a proton is symbolized as a 1 and a 1. Either answer is acceptable. All right. Nitrogen again, and this time we're going to carbon, but this time the mass does not change. The atomic number here is a 1. A 0 over a 1 You can symbolize it like that, or this is a positron. So this is how it is symbolized. I usually show the plus to make sure you know it's not a negative. You can leave that plus off, but it's called a positron. It was hypothesized when they discovered the electrons, and then they discovered it. Strontium is number 38. Deuterium is number 39. So because the mass did not change again, but this time it's a -1. So back to the question Tiffany asked. It's a question that's everybody's asking it. This side has to equal this side. So 39 minus 1 is 38. So this is a beta particle. You can also symbolize a beta particle as an electron. So, all right. Number 7, please be careful. Arsenic is formed. Arsenic is the product. The -77, the -210, those are the mass numbers. Arsenic is number 33 on the periodic table. The beta decay is still a product. So I gave you the product. I want to know, they call it, actually traditionally is called the mother and the daughter. This is all about instability. Yes, it's extremely sexist, but they called it the mother particle and the daughter particle. Now they call it the parent and the child sometimes, but when it was first done. All right, 33 minus 1, we must have started at 32. 32 is germanium. All right, these are all what's called, the whole page up to now is called natural decay. Every isotope for every element that is unstable, so not everything's unstable, carbon-12 is stable, hydrogen-1 is stable, but all the other reactants, what we started with, if it is unstable, it has a natural way that it decays, either alpha, beta, positron, proton, or a neutron it gives off to become more stable. Artificial transmutation is man-made. And this was during the 30s, 40s, 50s, 60s, and even now at the Big Hadron Collider in Europe, or at Fermi Labs outside of Chicago. Glenn Seaborg, he's on the periodic table. He did a lot of these. And so the lower part of the periodic table, these are all man-made. And they were made in his lab at Berkeley, California, in the United States. So that's how those got, and then they started naming them for famous scientists. So Einstein, Fermi, Mendeleev, Nobel, Lorentz. So these are a little bit different because if you notice, you have 2 things to start with. So what they're taking is 2 stable nuclei and they're ramming them together extremely fast. What's happening at CERN, it's 26 miles around, and they use magnets to get these particles going super duper duper fast, and then they wham them together. And they see what they can make, including the God particle, as it was called. It's quite fascinating. All right, so here is our equal sign. We do it the same, there's just 2 things on each side. So the 2 sides have to be equal. So 14 plus 4 is 18. So here I have 17 plus 1 to get to 18. My lower numbers are 7 plus 2. So that's a 9. And again, they're showing it as helium. Could be shown as an alpha. So 9 is the number I'm trying to get to. So 8 plus 1. So again, you can show it as hydrogen or a proton. So artificial, man-made, 2 things, and you get 2 new pieces. usually one small piece and then something that's unstable. This is how they keep making new elements. All right, oxygen is 8, hydrogen is 1. Again, this change it to an equal sign if that helps you. 16 plus 1 is 17, so 13 plus 4, and 8 plus 1 is 9, so 7 plus 2. Again, you get two choices. You can write it as helium, or it is an alpha particle. Again, I prefer alpha, but you can write it either way. All right, the next one I wrote out as symbols, so we're going to write it underneath, or I wrote it kind of, you'll see in the homework where I write it as a sentence, it's all words, and you have to change it to symbols. So aluminium, I don't know if I said that right, that's how everywhere else in the world says it. The United States, we're the only ones who say it weird. A neutron, remember, is a 0. It's neutral. The lower number is 0. The top number is mass. The lower number they often talk about is charge. All right, we get to sodium 24. 27 plus 1 is 28. And then 24 plus top will be 4. And so we see that 4, you're like, don't assume it's an alpha. Always do the math. 13 plus 0 is 13. So the numbers I'm circling are just what I'm trying to make the two sides equal. So it is our alpha particle. Questions? All right. This page has a lot of words. It is about two really important processes called fission and fusion. I'm going to skip to fusion first and come back to fission. Fusion is stars, or our sun. Our sun is a star. It is, right? Fusion means to fuse. So we're taking pieces. So we're taking small and we're going to bigger. The sun, 99.99% of all the elements in the universe are hydrogen, because the mass of all the stars is pretty much, you can ponder this. And so what's going on in our sun is hydrogens are colliding and they are forming helium or lithium. There's actually a whole sequence of how they form. And the mother lode of energy. So where does it occur was in the stars, and this is billions and billions of kilojoules. We're going to talk about moles on Wednesday. The problem is the temperature, and at that temperature, atoms are no longer nuclei with electrons in them. They become fluid. So they become like one giant atom, and so things are moving around more fluidly. And so that's why it says the nuclei are unbound. So it was considered a fourth state of matter. There's actually now at least 9 states of matter. We're only going to deal with solid, liquid, and gas in here. But when we get to these crazy temperatures, it turns out in the universe, they have theories that there's all these other types of matter. They actually can get to this temperature here on Earth in special labs. This is a fusion collider or a fusion reactor, and they can contain the plasma. I don't know how they do it. The problem is they haven't been able to tap into it to put it into our grid so we get the energy means electricity. So we're changing, we got to move a turbine. So like the water moving over Bonneville Dam, we have to get this energy to move a turbine. The turbine moves inside a magnetic field and we can recover the energy. They're right on the verge of it. All right, So fusion happens in the stars and on the sun. It will be unlimited energy. There's also a whole political thing there because the people who have power with energy would lose their power. There's lots of movies about that. All right, fission is splitting the atom. So splitting the nucleus. Fusion is bringing them together. Fission is splitting it. These are the people who figured it out. Their pictures are here. And so what normally happens, most things, if you send a neutron at most elements, they just become more mass. They just keep getting, so it'd be like if I sent chocolate at you and you, or a Big Mac, and you ate it, you just become bigger and bigger and bigger. But what happens, very rarely, but it does, uranium-235, if you send a neutron at it, it actually splits. And I'm telling you on this question, it splits into barium and krypton and something else. So this is fission. Fission has to have the neutron. So you're splitting the nucleus with a neutron. Very few things will go through fission. That's a good thing. This is what our nuclear bombs, so atomic bombs for a fission bomb, and the hydrogen bomb, which has never been used, is a fusion bomb. Uranium was number 92. Barium is number 56. Krypton is number 36. So our lower numbers are 92. When you add these two up, you get 92. You're left with 0. When you add the top numbers up, you get 236. When you add these up, you're missing 3. You need 3 more to get to 236. You use your calculator. To have a 0 on the bottom, it has to be a neutron. So you don't write 3 over 0. You have to actually say, I get 3 neutrons. So this is called, and I know I'm going fast, but I'm managing. You can always go back and watch the video and rewind. You'll get it. This is known as a chain reaction. We started with a neutron. We made more neutrons. So what happens in an atomic bomb, these are separated on impact. The neutron, they only have to have 1 neutron, hits 1 atom of uranium. It splits it, but it makes more neutrons. This is all happening in less than 10 to the negative 15th of a second, right? These 3 now split 3 more. They each make more. And so in less than a nanosecond, millions of these billions, quadrillions have happened. You get huge amounts of energy released. Fusion still wins. And so again, the energy is released. I don't have, my notes are sitting over there of how much this is. This is like 1 billion tons of coal or something like that. It doesn't release greenhouse gases. It doesn't change the pH of the atmosphere. The controversy is the waste is radioactive for billions of years. So the waste is radioactive, meaning it's giving off alpha or beta or gamma particles. And I guess there's 3 pieces. Another controversy, if you look at Japan, and when they had their nuclear power plant that melted down, when an accident happens, it's big and it's bad. And used to teach a general science class, and we talked about global warming. This is 25 years ago, where nobody believed in it, right? So we talked about the greenhouse effect. We talked about acid rain. We talked about all these environmental issues. And then we talked about nuclear, and they had to write an essay that your town, your city has grown. They're going to build a new power plant. What type do you want? Do you want coal, which is going to cause the greenhouse effect, or do you want nuclear? And everybody in the class picked nuclear because it's considered green energy, except one student, and she was from the Ukraine. This is 25 years ago, so she was old enough to have been there when Chernobyl happened. And every female in her family was dead from cancer. And she also had, I believe, her uterus removed because of cancerous growths and stuff. And so it's not good. So you can cause the meltdown, disaster. And then, can man be trusted? So actually, a really cool story is I had a student one year, element number 43. Oh, let me see on mine. Yeah, so this one from, sorry, it's glaring. To find. The yellow ones are man-made, and he was asking me, why is that one yellow? And I said, well, 43 is just an unstable number. They cannot make, there's no stable form of TC. So it's actually called technetium because it's man-made, so technology. And so he decided he wanted to do a paper on it, and he went to research it. And this is fascinating that this student wanted to do it. And as he's researching it, he realizes every paper was written by his grandfather. So his grandfather had been part of the Manhattan Project. And so for extra credit, he interviewed his grandfather and showed the videotape to the class. So talk about like an unfair extra credit opportunity, but it was phenomenal. He was 90 years old then. And the stories he told us in this video were crazy about some of the stuff that went on. So anyway, that was really fascinating and fun. And he was told when he died, his body had to be left to the US government because they had to see some of these guys were exposed to huge amounts of radioactivity and they were still alive. So kind of like me, Captain America today. All right, I could talk about all this stuff forever and ever. Units, says FYI, those are for your information. That's Glenn Seaborg. The biological effects. By the way, radiation treatment, whether pros and cons, works for mass tumors, and it's become pretty amazing because they can really localize, pinpoint. My mom had breast cancer and she went through radiation treatment, and all she ended up with was a little itty bitty sunburn spot after the 20-some treatments that she could drive herself to. But large exposure, the places that are going to be affected the most is your GI, so your intestines. So people who go through radiation treatment will often have nausea, your blood, and that is because these are the parts of your body that turn over. The cells have a rapid turnover time, but your blood is your immune system, and so when you're going through radiation, you want to be careful being exposed to people with colds and stuff. It's kind of like what we're all going through now. And also it is your energy because your red blood cells. So if your red blood cells are affected, that's just what RBC is, red blood cells. And then the other is reproductive, because if they would never do radiation treatment for tumors that were in your reproductive area, especially if you were wanting to have children, because you could affect, pass on any changes to offspring. Again, the best defense is you walk away, because the further you get away, the less your exposure. I'm going to move. What you need to know from this page: fission means plus a neutron, and you split it. This is what I forgot to say. There are something like 350 ways it splits. uranium-235. You cannot predict how it's going to split. It doesn't split it in half. The neutron just hits randomly. It always splits into two pieces that add up to 92, and you always get neutrons. Sometimes it's 2, sometimes it's 3, sometimes it's 4. So you will always be told 2 of the pieces, and you'll find the third. And then fusion is bringing things together, and that's in the stars. All right. So last thing we have to talk about is half-life. So half-life is how long this is around. So how long to the decay? And it varies. So some of the elements, like polonium, a lot of these man-made ones down here, they have extremely short half-lives, like microseconds. So I don't know how they even know it's there. It's a blip on the computer screen, but then it breaks down really fast. Other ones like uranium are billions of years, and that's how they come up with the ideas of how old the Earth is, and dating of stuff is looking at these different samples. Bismuth is trillions of years that its half-life is. So it's how long, and actually, to give you an even better definition, it's how long for half of the sample to decay. So we'll just go how to solve. There's 4 variables. There is time total. There is the half-life. The half-life is either going to be given to you or you're going to solve for it. It is different for every element and for every isotope of the element. The symbol is T1/2. It's just a symbol saying half time, so half-life. There is your starting amount, and there's your ending amount. So there's 4 pieces of information. 2 of them deal with time, either the total time or the half-life, and 2 of them start with how much you have. So let's just walk through it. There is a fancy, dancy mathematical formula. I'm not going to do it that way. I know it. It does require you to use natural logs and little e, and some of you know what that is, and some of you are like, what's a natural log? So we're going to do it a much simpler way. So this is just saying fluorine 18. This is the half-life. And it says you start with this much, and it wants to know how much after 8 hours. So the 8 hours is the total time. The time has to be the same unit. So 120 minutes, pretty sure you all know that is 2 hours. It's the length of our class. Okay, so if you take the total time, you don't have to show this, divide by the half-life. So we have 8 hours. This is my total time. Divide by my 2 hours, we will get that there are going to be 4 half-lives. We're not done. That's not what my question asks, but this is key, that there's 4. In this class, the number of half-lives is going to always be a whole number. You can, of course, not be all the way through a half-life. This graph up here, you don't need to know. It's showing you at a half-life, half of it's there, now half again, and it keeps cutting in half, and keeps cutting in half, and keeps cutting in half. When I worked in the lab, we worked with radioactivity. Once something went through 3 half-lives, it was considered we were allowed to ship it back to the place that took care of it. But we had to hold on to it through 3 half-lives. So we had a special place that we kept stuff. It is not a linear relationship. It is a logarithmic. What we're going to do is we're going to start with 1 milligram to start. And we're going to cut it in half. So this is my first half-life. So now I have half a milligram. That's all it means. Each half-life, you cut it in half. And then my next half-life, I cut it in half again. So half of 0.5 is 0.25. And then I'm going to cut it in half again. I can't believe I did 4 half-lives. All right, and then the fourth one, cutting it again. You can have your calculator. 0.0625. So you can always cut it in half. You could also do it, you can also do it as a fraction. So this would be 1/2, 1/4, 1/8, and we would now be at 1/16. Some people like fractions. I went with a number. So there's my final answer. If we had a nice box or a blank, that would go in. So you just cut it in half. All right, we're going to do a different one. This time we're going to solve for the half-life. So that's my question. Strontium 90. So by the way, strontium is very dangerous to work with. Strontium is right below calcium. This was a question on your first worksheet. Families behave the same. Families tend to accumulate together. If you get exposed to strontium or barium from that fission reaction, they end up where calcium is in your body. And I know several of you want to go into dental hygiene. Most of the calcium in your body is in your bones. And so the radioactive material accumulates in your bones. Your bones is where your blood is formed, and your blood is very susceptible to that. And so a lot of blood cancers. So after Hiroshima and Nagasaki, it was lots of people with leukemia and other blood cancers. All right. So 86.4 is the total time. We're starting at 4 grams. So you're going to always just cut in half. So I go to 2 grams, I go to 1 gram. How I know when to stop is I get to the final answer, and I told you I wanted you to get to 0.5 grams. So you're either going to be solving for the final amount, or you're going to cut in half until you get to it. So I cut in half 1, 2, 3. So again, you start, cut it in half, cut it in half again, cut it in half again. It took us 3 half-lives. So 3 half-lives. The total time is 86.4 years. So we take 86.4 years and we divide by 3. And that gives us somewhere around 27. I think it's like 26.8, but we're around 27 years. So it took 27 years for the first half-life, another 27 years for the next one, and another 27 years. And again, if you want, you can go with the 3 sig fig rule and just give your answers with 3 sig figs, but as long as we're around 27 years. All right, we're gonna go, so here's Podwang Penguin. Can't really see him, he's huge. He went to the nuclear power plant. He's like Bruce Banner, he's a huge penguin. So I apparently look cute and fluffy because students buy me lots of stuffed animals. So my room is filled with all the stuffed animals that were lonely and left at school. Hanford is upriver from us. It's actually really fascinating. I haven't been there. I've been very close to it. So there is a motocross racetrack. And when you're at the motocross racetrack, if you walk up on the hill, you get a perfect view of Hanford. Really fascinating. If you go on the road, you can't get anywhere near it. Anyway, you can read all my words and go, oh my gosh. All right, he's at 12.5%. So what happened, this is the carbon dating one. Sorry, I had to read where I was going with this. And I put it on here to do the example with you. It used to be on the study set. Maybe it's on the study set. So what happens with carbon 14, you don't have to write this down, is we have carbon 12 and carbon 14. You and I are always exposed to both. We are eating, when we eat food, we get carbon. We get carbon, hydrogens, and oxygens, a little bit of nitrogen and phosphorus. Most of the carbon is carbon-12. Some of it is carbon-14. You and I are still alive. We're always taking in more carbon. And so this ratio stays the same. Once you're dead, in case you didn't know, you're not taking in any more food. And so you're not getting any more carbon in. What happens, you're not getting any more carbon-14. The carbon-14 decays. The carbon-12 just stays there. It's really stable. So the amount of carbon-14 decreases, this ratio changes. And so that's what they're able to measure. So if they find an old, it has to be something that is made of carbon. So when they find a relic, if it has carbon in it, they measure the carbon-14. And so this carbon-14 is 12.5% of what it would be today. So today it would be at 100% of normal, whatever that number is, it doesn't matter. After one half-life, it would now be at 50%. That half-life is maybe 5,730 years, roughly. These are all actually not very precise. It's like a number they throw out there. This is not rocket science, but it allows us to make estimations. All right, after the next half-life, you have half of 50. So you would now have 25%. So this is another 5,730 years. So now we're at like 11,000 some years. And then after another 5,730 years, now you're at 12.5%. Now, you still have the carbon-12 is there. It's the carbon-14 that decays. So we went through 1. The arrows are your half-life. 2, 3. So the question was how many half-lives? We went through 3. So we went through 3 half-lives. So the turkey bone he found was from 3 half-lives ago. So if we take 3 times 5,730 years, we get that. That's how old his unicorn or dragon bone or whatever you want to imagine. Yeah, so he compared it to his Thanksgiving turkey. So, there we go. That's a tough question. You have like 2 of these at the end of your homework and 1 on your worksheet. And I will be here in my office hour. I will hang out until 9 o'clock tonight. If people are working on today's worksheet, and I will be here on Wednesday before class. If you have questions, I will go through the study set. Again, the study set is due at 6. Your study set, you get the 5 points that you made your best effort, that you tried everything. The worksheet, I do grade on it being right, but realize it is only a total of 6 points. And so, you know, you might lose a quarter of a point. So if your sig figs are wrong, you might lose a quarter of a point. So don't lose sleep over the little things. Is there any questions before I stop recording?
I just want to touch on question number 3. So you have 27 years, but I put it in my calculator and it's 28.8.
Oh, you know why? You're right. It's 29. That was me doing 27 divided.
Make sure just in case that it confused anyone else.
Yeah, you know, I thought I put all the answers on this page, and I did down here. I want to remind, thank you, Christy, for that. You know, oh, and there's my calculator. I just found it. I know why I did that. I did a reverse math thing in my head. I'm fascinated by myself because when I do this on a chalkboard, I can do math much better, apparently, than I can on a piece of paper. Anybody else questions? Yeah, so it's close to 29 years. It's good for your teacher to make mistakes like that. Was that Christy? You get a heart too. Put her name up there.
Extra points, yes.
Oh yeah, right? The teacher, I can't throw apples to you all to have, or oranges, or eggplant. Anybody wants eggplant? Anybody else? You can stop recording.